Imagine you're in a bustling cafe, and multiple voices are overlapping. How does your smart speaker know exactly who's speaking? That's the magic of speaker tracking, identifying voices, pinpointing their location, and matching them to identities. But here's the challenge. When people overlap, move, or speak in short bursts, traditional systems stumble. Today, we're unraveling a groundbreaking approach that makes speaker tracking faster, smarter, and more robust. Traditional systems rely on long, continuous audio snippets to assign speaker identities. But this creates a problem. Short speech fragments or overlapping voices confuse the model. It's like trying to follow a soccer game by only watching 1-second clips. You miss the flow and get lost in the chaos. These systems struggle with real-time applications like video calls, where delays and errors are unacceptable. So how do researchers fix this? The answer lies in short context speaker embeddings, compact voice, fingerprints, extracted from brief audio chunks. But how do you make these fingerprints reliable when speech is fragmented or overlapping? Let's break it down. Enter knowledge distillation, a technique where a simpler model, the student, learns from a more complex one, the teacher. The teacher, trained on vast datasets, excels at recognizing voices even in noisy conditions. The student, meanwhile, mimics this ability, but focuses on short, noisy audio blocks. It's like a student learning to solve math problems quickly by observing a master's slow, deliberate process. To refine this, the system uses beamforming, a tech that isolates sound from specific directions, like a microphone listening to one person while filtering out others. This reduces overlap, giving the student model a clearer signal to work with. But here's the breakthrough. Instead of analyzing long audio segments, the system processes fixed-size blocks of sound. Think of it as breaking a conversation into 250 ms to 6-second chunks. This reduces latency, making the system faster. However, smaller blocks mean less context, so overlapping speech can still trip things up. The key innovation is blockwise identity reassignment. Unlike traditional fragment-based methods, which analyze short, isolated snippets, blockwise processing streams data continuously. For each block, the system extracts a speaker embedding, a mathematical representation of the voice, and compares it to a library of enrolled speakers. By adjusting block sizes, we balance speed and accuracy. Shorter blocks mean lower latency but less context, while longer blocks provide more data but risk errors if speakers move. Experiments show this method outperforms older techniques. In datasets with simulated two-speaker conversations, blockwise reassignment boosted accuracy by up to 25%. Even with shorter blocks, the system remains surprisingly reliable. It's like a detective solving a case with just a few clues, still sharp even if not perfect. Let's compare the student and teacher models. The teacher, a complex pre-trained model, excels with long 6,400 ms chunks. The student, a distilled version, shines with the shortest 250 ms blocks. But here's the twist. In the middle range, 803,200 ms, the student outperforms the teacher. Why? It's better at handling overlapping speech, like a listener who focuses on the right voice even when others talk over it. A critical finding, fragment-level reassignment, analyzing audio from the start of each snippet, scores higher than blockwise methods. Starting at the beginning reduces overlap confusion, while random start times in the middle of a snippet increase errors. Blockwise methods, though simpler, can't recover as well from mistakes. Once a block is misidentified, the whole tracking process falters. This research has huge potential. Improved speaker tracking could revolutionize voice assistants, transcription tools, and even robot social interactions. But challenges remain, especially with simultaneous speech. So the next time your smart speaker gets who's speaking, remember, behind the scenes, algorithms are working hard to decode the noise. Thanks for watching, stay curious, and let's keep exploring the science behind the tech.